Okay, we've been talking about horizontally launched projectiles. Now I want to talk about a projectile that's launched at an angle. So it doesn't just have a horizontal velocity to begin with, it has a velocity at an angle to begin with. So we have to take into account horizontal velocity and vertical velocity. So if we look at this right triangle represents the velocity vectors. The green vector is the velocity that projectile is launched at. The blue vector is the horizontal component of that velocity, and the red vector is the vertical component of that velocity. Now remember, the vertical component of velocity changes due to gravity. The horizontal one does not. So when we want to solve for these, we can break them up into horizontal motion, vertical motion, and we get the same exact formulas that we had. So if you want to, you can solve for initial vertical velocity by just taking v0 sine theta, if you know the initial velocity and the angle it's headed at. And you can solve for the horizontal velocity. Note we don't have v0x, we have vx because it's the same no matter what, by just taking VO cosine theta. And then you can plug those into the original formulas that we have our one-dimensional motion formulas. And the vertical one has acceleration, the horizontal one does not. We can also just substitute the VO cosine theta or VO sine theta into the formulas so we don't have to do two calculations. We can just substitute and do one calculation. So down below here, I have the delta x equals VO cosine theta times t. That's our horizontal distance that a projectile travels, as long as we know time, and the initial velocity. The delta y equals VO sine theta t plus 1/2 gt squared. That's the vertical displacement the projectile has at a certain time in its flight if we know the initial velocity and the angle. Likewise, we can solve for the horizontal velocity at any point. Now, the horizontal velocity at any point is equal to the initial horizontal velocity. So that's what we see Vx equaling, or the vertical velocity at any point. Now, if we are asked for a velocity at a certain point, we're asking for V, no subscript whatsoever. And V would just be the hypotenuse of a triangle that has Vx and Vy. Notice there's no zero there because the zero represents the initial instant that it becomes a part of projectile. And when we don't have a zero, it just means at a point that it is moving. So they would be happening at the same exact moment, Vx and Vy, and then we can find V. And we can also find theta. So we have to work backwards or forwards depending on what we're looking at. If we know the horizontal and vertical components of motion, then we can find the original motion and the angle it's moving at. If we know the actual motion, we can break that up into horizontal and vertical components. And so we can work either direction. You might be asked where something is, you might be asked how fast it's moving, you might be asked what angle it's moving at. So, and it takes practice to do these things. So that's what we do. We're doing the same exact formulas. Now we're talking about them in horizontal and vertical detail a little bit differently. All right. So we still get a parabolic motion. So if you look at this trajectory, here's an object that is flying through the air. The red dots represent 1 second, 2 second, and 3 second. So every 5 dots is a second worth. So I'm going to ask at the end of this, take a good look at this. I'm going to ask one of the questions is how fast is it actually going horizontally? How fast is it actually going vertically? And think about how you would solve that type of thing. The horizontal is easier than the vertical because vertical is accelerated. So we get this typical trajectory of a parabola, but this also gives us a way to estimate how fast it's moving horizontally, how fast it's moving vertically at the instant that becomes a projectile. All right. So this the parabola, some things are really helpful in remembering what's going on with this. One thing that we can do is, so there's our initial velocity. So remember, initial velocity is how fast it's going the instant it becomes a projectile. So that's not telling us where something's going to end up. It tells us what direction it's pointing at and how fast it's going when it becomes a projectile. And then we get the parabola that happens below that angle because that would be the highest angle that it would happen at. and the parabola occurs below that. This formula here is called the range formula. This is done by combining the angle and the initial velocity to get, and our previous formulas to get a delta x for a given velocity. So basically they solve for time and put it in the delta, solve for time using vertical motion and put it in the delta t, or the time portion of the horizontal motion, to solve for delta x. This only works if the total delta y is 0, if it lands at the same height that it started at. This formula is not good for any other situation. So our situation that we have with our example of kicking a soccer ball that you're going to see for today is one of these examples that it lands at the same level that it started at. So you can use that information. Now, other information when it lands at the same level it started at, half the time it's in the air it takes to go up to the top. So if you know how long it's in the air, you can divide that in half, and you know how long it took to get to the highest point. At the highest point, it is not moving vertically, but is still moving horizontally. So you can treat that as if it's dropping from that highest point, like it's a horizontally launched particle from the highest point if you wanted to, and use what we've done in horizontal launch things. But you have to remember that that's half the time that it's in the air. So we get the symmetry working for us in that. So this is showing us how the range changes based on the angle. And if we change the angle, there's actually two different angles that would land at the same spot. And both those angles are the same angle away from 45 degrees. So if I shoot something at 30 degrees at the same speed as I shoot something at 60 degrees, they're going to land at the identically same spot, the same distance. The range is the same. At 45 degrees, the range is at its maximum. And we can prove that mathematically if we need to. We might do that in class, I doubt it. But that's kind of something that you guys have an inherent idea about. Now, this is, again, when we disregard air resistance. If air resistance is there, the maximum range would be at an angle a little bit less than 45 degrees, somewhere in the high 30s, low 40s, because it would be traveling faster horizontally than vertically, and it would get farther by the time the air resistance really starts slowing it down. So basically what you have is a trade-off between horizontal motion and vertical motion. If you shoot it below 45 degrees, it's moving faster horizontally, but it's not in the air as long. If you shoot it above 45 degrees, it's in the air longer, but it's moving slower. So it has more time to travel horizontally, but it's not moving as fast horizontally. So you're trading off one for one. So the 45-degree angle is your best angle, and that's given to us by this maximum range formula. If we know the initial velocity, we can square that and divide it by 9.81, and that would give us the maximum range. And that's using this previous range formula and setting it for 45 degrees, because sine of 2 times 45 degrees, sine of 90 degrees is 1. All right, so that is our mathematical relationship there. All right, so that symmetry in projectile motion is really critical. We can find the velocity at any point in this. If we know the vertical velocity, we know that it's going positive on the way up, negative on the way down, but the actual magnitude of the velocity is the same. It's the direction that's different. So when it's going up, if it's going at 10 meters per second at a certain point, then when it's passing that point on its way down, it's going 10 meters per second downward. So that would be a difference in the vertical portion. The horizontal portion stays the same, the horizontal component of velocity. So we get the same triangle. It's just the theta is either above horizontal or below horizontal. So when something lands, it's going at exactly the same speed and exactly the same angle as when it takes off if it lands at the same level. It just happens to be going downward instead of upward. So that symmetry is helpful when we're trying to solve some problems, and it'll come into play on some of the problems that you have from the book that we're working on this week. So in general, and this is just a summary of all projectile type stuff, the components in the X and Y directions can be treated independently. That means the horizontal displacement and vertical displacement, and the horizontal velocity and vertical velocity. Now, we tend to combine horizontal and vertical velocities into a right triangle. We don't do that with displacements unless we don't want to know exactly how far away it is from where it started. We're rarely asking that. That's not the path that the projectile takes. The path that the projectile takes is parabolic, which we have in the fourth bullet point here. And the reason is because of the acceleration downward. So as long as we take into account gravitational acceleration and vertical motion, we can do that. Keep in mind, if the launch angle is 0, we only have a Vx, we don't have a Vy 0. So we don't have to use our formulas with a Vy 0. So it simplifies our formulas. So sometimes I try to figure out, okay, if I know how long it's in the air, I cut that and it lands at the same level it started at when I shoot at an angle. I cut that time in half, and then I treat it like it's shot horizontally. Then I don't have to worry about an initial vertical velocity. If I find my final vertical velocity, that would be the opposite direction of my initial vertical velocity. So there's different little shortcuts that can help for doing that as well. And then our term for range is a horizontal distance that something travels. Most specifically, it is the distance it travels when it lands at the same level that it started at. Now, we can do range at different levels. We just can't use the range formula. We have to use a delta y that is not 0. And when delta y is not 0, we can still solve for time. It just starts higher than it ends, or it starts lower than it ends. And we just have to take that into account. So we can't cut the time in half in those situations, which makes it a little bit more complex. All right. Work on the book problems for next week, and keep working on understanding this. We'll have a little assignment here looking at a soccer ball that's kicked and asking some questions about that. And eventually we'll talk through how we solve those things. All right. Have a great day. See you later.